In the previous class, we have discussed about the linear function of the multiple random variables, right? Do you remember that? So today, we are going to first solve the example 5-33. This is about the beverage volume. Soft drink cans are filled by an automated filling machine, and the mean fill volume is equal to 12.1 fluid ounce. Okay, this is the unit, and the standard deviation is equal to 0.1 fluid ounce. So from the example, we know about the mu. Mu is equal to 12.1 fluid ounce, and also the sigma, which is the standard deviation, is equal to 0.1 fluid ounce. So assume that the fill volumes are independent, okay? And also the fill volumes follow the normal distribution, which means that the fill volumes are the normal random variables, okay? This is the assumption. And for this case, what is the probability that the average volume of 10 cans is less than 12 fluid ounce? That is the example. So to solve this, we have to assume the random variables, that is, let x1, x2, blah, 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 x10 denote the fill volume of each can. Okay? And also, x bar is equal to the average fill volume. Okay? And since the fill volumes follow the normal distribution, this average value also should follow the normal distribution. Okay? So for this case, the question was the probability of x bar, average, right? Average volume of 10 cans should be smaller than 12 fluid ounce. That is the question. Okay? So, since the average fill volume is following the normal distribution, we can change the x bar to the standard normal random variable z. Okay? To use the appendix table. And this should be smaller than 12 minus the mean of x bar, okay, over root the variance of x bar. Okay? So we need to calculate the mean of x bar and also the variance of x bar. Based on the previous class, what is the mean of x bar? That is equal to mu, okay? And the variance of x bar is equal to the sigma square over p. Please see your previous slide, okay? So mu is equal to 12.1 here. And the variance of x bar is equal to 0.1 square over 10, because p is the total number of variables. So this is equal to 0.001. Okay? So this is equal to the probability of z when z is smaller than 12 minus 12.1 over root 0.001. And this is equal to the probability of z when z is then minus 0.1 over 0.0316. Okay? And this is equal to the probability of z when z is smaller than minus 3.16. And if we use your appendix table, you can simply obtain the answer, that is 0.00079. Okay? So the answer of this example 5-33 is 0.00079. Okay? So now we can solve the example 5-33. So up to this slide, we have discussed about the linear function of the multiple random variables, right? But there are also nonlinear functions such as polynomial function, and also the exponential function, and also there is a log function. Okay? So we can say this is the general functions, okay, of the non-random variables. So we are going to deal with the general functions of the multiple random variables in this slide. A linear combination is not the only way to form a new random variable y from one or more random variables xi, right? So in this case, the transformation function can be used, and the transform function should satisfy the following two properties. The first one is that each value of x produces exactly one value of y, and also each value of y translates to only one value of x. Okay? So these properties should be satisfied to use the general functions of the multiple random variables. And this can be understood in the following example. So now we have two options. The first one is that the discrete random variable, and also we have the continuous random variable, right? So we have two options. So in this slide, we are going to first deal with the discrete random variable case. Suppose that x is a discrete random variable with the probability mass function of fx. Okay? And this means that the fx is given in the example. Okay? And let y is equal to hx. This is the general function, not a linear function. And define a one-to-one transformation between the values of x and y, so that the equation y is equal to hx can be solved uniquely for x in terms of y. Okay? Because the values of x and y are the one-to-one transformation can be defined as one-to-one transformation relationship. So let this solution be x is equal to uy. Okay? Then the probability mass function of the random variable y can be given the following equation. The probability mass function of y is equal to the probability mass function of x when x is equal to uy. Okay? So in the example, the probability mass function of fx is given, and is equal to hx is also given. So for this case, we can calculate the probability mass in the case of the general functions. And this is the example, and you guys can understand based on this example. Let x be a geometric random variable with the probability mass function of x that is equal to p by 1 minus p to x minus 1th power. Okay? For this case, x is from 1 to infinite. And in the case, find the probability distribution probability mass function of y when y is equal to x squared? That is the question. So, based on the previous slide, the definition is as follows. The probability mass function of y is equal to the probability mass function of x when x is equal to uy. Okay? And also, y is equal to hx, and hx is equal to x squared. Okay? So, we need to calculate the uy first. Okay? So, what is the uy? The definition of uy is equal to x. Okay? In the previous slide, s was defined as the uy. Okay? So, x is equal to uy. Okay? And that is equal to root y from the above equation. Right? Because y is equal to x squared, so y is equal to root y. Okay? So, uy is equal to root y. Okay? This can be defined because these two random variables can be defined as one-to-one transformation relationship. Okay? So, for this case, we know about the probability mass function of x here. Fx is equal to p by 1 minus p by x minus 1. Okay? When x is from 1 to infinite. Right? So, the probability mass function of y is equal to the probability mass function of x when x is equal to root y. Okay? So, that is equal to p by 1 minus p to root y minus 1th power. Okay? When y is equal to 1, when x is equal to 1, here, y is also equal to 1. When x is equal to 2, y is equal to 4. And also, when x is equal to 3, y is equal to 9. 9, blah, blah, and infinite. Okay? So, this is the probability mass function of y. Okay? That is equal to p by 1 minus p to minus root 1 minus p to root y minus 1th power when y is equal to 1, 4, 9, blah, 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 and infinite. Okay? So, this is the answer for this example 5-36 for the case of the discrete random variable. Okay? And now, we are going to also discuss about the general function of a continuous random variable. Okay? We have two random variables. The first one is the discrete one. The second one is the continuous one. So suppose that x is a continuous random variable with the probability density function of x, fx, and the function of y, when y is equal to hx, define a one-to-one transformation between the values of x and y so that the equation y is equal to hx can be uniquely solved for x in terms of y. So this is the identical explanation with the previous discrete case, but only difference is that the discrete random variable is changed to the continuous random variable. So let this solution be x is equal to uy, and probability distribution of y is given the following equation. Okay? So for the case of the continuous random variable, the probability density function of y should be equal to the probability density function of x when x is equal to uy by the absolute value of Jacobian. Okay? And here, the Jacobian is equal to u prime y. That is the differential value of uy. And that is called the Jacobian of the transformation. And also, the absolute value of Jacobian should be multiplied here. Okay? So this is the definition of the general function for the case of the continuous random variable. So please remember this equation. Then we are going to solve another example, 5-737. This is about the function of a continuous random variable. Let x be a continuous random variable with the probability density function of x that is equal to x over 8, okay, when x is between 0 to 4. So in this case, find the probability density function of y when y is equal to 2x plus 4. So to solve this, we need to know about the relationship, that is the probability density function of y is equal to the probability density function of x when x is given as uy by the absolute value of Jacobian. Okay? And in this case, y is equal to 2x plus 4. Okay? So, y is equal to y minus 4 over 2. Okay? Right? And that is equal to x. So, the Jacobian is equal to u prime y. Okay? This is the differential value. That is equal to 1 over 2 here. Right? So, this can be given the following equation, that fx is equal to x over 8, right? So the x should be replaced with the uy, okay? So that is equal to y minus 4 over 2 over 8, okay? X is just replaced with the uy here. And by the absolute value of Jacobian, that is just 1 over 2, okay? Because this is the plus value. So 1 over 2. So this is equal to y minus 4 over 32 when y is between, when x is equal to 0, y is equal to 4. Right? When x is equal to 0, y is equal to 4. So the y should be between 4. And when x is equal to 4 here, the y is equal to 12. Okay? So y should be between 4 and 12. Okay? So this is the probability density function of y when fx is given, and also the relationship between the x and y is given. Okay? So this is the answer of the example 5-37. Okay? So this is end of chapter 5. And now, we are going to start a new chapter. This is the chapter 6, about the explanation of sampling. And this is the chapter outline. Okay? firstly, we are going to study about the numerical summaries. And secondly, we are going to learn about the stem and leaf diagrams. And then we are going to study about the frequency distributions and the histograms. And then we are going to study about the box plot and time sequence plot. And finally, the probability plot will be discussed in this chapter. So this is the outline of the chapter 6. Okay? So this is quite easy chapter, actually. So this is the learning objectives for the chapter 6. After careful study of this chapter, you should be able to do the following. Firstly, you can compute and also you can interpret the sample mean and sample variance and sample standard deviation and sample median and also the sample range. Secondly, you can explain the concepts of the sample mean, sample variance, and the population mean, and also the population variance. And then you can construct and interpret the visual data displays. This is very important factor for the engineers, including the stem and leaf display, and also the histogram, and also the box plot. Okay? So you know how to learn, you will learn how to use these skills in this chapter, okay? And first, you can explain the concept of the random sampling, and also you can construct and interpret the normal probability plots, and then you can explain how to use the box plots and other data displays to visually compare 2 or more samples of the data effectively. And finally, you know how to use the simple time series plot to visually display the important features of time-oriented. So these are the learning objectives of the chapter 6. Okay? The first, we are going to discuss about the numerical summaries. Well-constructed data, summaries, and displays are essential to good statistical thinking, right? And data are the numeric observations of a phenomenon of interest. And the totality of all observations is a population, okay? And a portion of the population which are used for the analysis is a random sample, okay? So the total of observation is a population, and a portion of the population is the random sample, okay? So random sample is included in this population, okay? And the center is measured by the mean, and also the spread of the data is measured by the variance. So this is the definition of the means. If the n observations in a sample are denoted by x1, x2, blah, 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 xn, the sample mean is given the following equation. X bar is equal to x1 plus x2 plus blah, 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 plus xn over the total number of samples, n here, okay? And this can be written as here, the summation of I, when I is from 1 to n, xi over the total number of samples. We already know about this, right? And for the n observations in a population, the population mean, which is similar to the mean of the previous probability distribution, denoted as mu, with equally likely values, which means that each random variable has the equal probability. And the probability mass function of fxi is given this equation 1 of the total number of observations, right? Because this is the equally likely values. And for this case, the population mean can be given as the following equation. So mu is equal to the summation of I when I is from 1 to large n, x I by the probability mass function fxi. Okay? So in this case, what is the summation? What is the fxi? That is 1 over large n. Okay? So this can be written as the summation of I when I is from 1 to large n, xi over large n. Okay? So for the case of the population, the mean, okay, the equation of the population mean has an identical formulation with the equation of the sample mean. But the only difference is that the small n is changed to the large n. So this is the example 6-1 about the sample mean. Okay. Consider A observations of pull-off force from engine connectors in the previous chapter 1. The 8 observations are summarized in the table as you can see here. The I is from 1 to 8 and xi is from 12.6 to 13.1. So in this case, what is the sample mean? That is very simple. For this case, the x bar sample mean is equal to the summation of I when I is from 1 to 8, right? Because we have 8 samples, xi over 8. Okay? So this is equal to the summation of 12.6 and 12.9 blah 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 plus 13.1 over 8. Okay? And this is equal to 104 over 8. That is equal to 13 pounds. For this case, the unit is pound. Okay? So, based on the previous definition, we can easily calculate the sample mean when we obtain the data from the experiment. Okay? And now, we are going to learn about the definition of the variances. If x1, x2, and xn is the sample of n observations, the sample variation is given the following equation. That is s squared, this is the sample variance, that is equal to the summation of I when I is from 1 to small n, xi minus the sample mean, okay, x bar, square over n minus 1. Okay? So this is the definition of the sample variance. And also, similar to the sample variance s squared, the variability in the population n is also defined by the population variance, that is the sigma square. That is given the following equation. Sigma square is equal to the summation of I when I is from 1 to large n, xi minus mu, this is the population mean square over large n. Okay? So please remember these two equations, okay, to solve the example. And this is the definition of the standard deviation. The standard deviation is the square root of variance. So sigma is the symbol of the population standard deviation. Because the population variance was the sigma square, so the root sigma square is equal to just the sigma. And also, S is the symbol of the sample standard deviation. Okay? The sample variance was the S square, so root S square is equal to just S. So the unit of the standard deviations are the same as the data, right? And also the mean, okay? So this is the example of the sample variance. Table 6-1 here displays the quantities which are required for calculating the sample variance and the standard deviation for true or false data. Okay? So based on this table, we can calculate the sample variance and the standard deviation, sample standard deviation. So the sample variance S square is equal to the summation of I when I is from 1 to small n xi minus the sample mean square over small n minus 1. Okay? This is the equation. And this is given that the summation of I when I is from 1 to 8, right? Because we have 8 samples here. xi minus, what is the sample mean for this case? We have already calculated, right? That is 13 pound square over 8, okay? Oh, sorry, 7. So this is equal to 12.6 minus 13 square plus and 12.9 minus 13 square plus blah 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 minus 13 square over 7. And this is equal to 1.6 over 7, okay? So this is equal to 0.2286 pound square, okay? So this is the sample variance. And what is the sample standard deviation? That is roots of variance, right? S square. So that is equal to the root of 0.2286. That is equal to 0.48 pound. Okay? So this is very simple example because we already know about the mean and variance. So this slide is explaining about the computation of the sample variance S squared. The previous calculation for the sample variance is quite complicated. Why? Because the equation includes the mean. Sample mean x bar, okay? So to solve this equation, we first calculate the x bar, right? So it is quite complicated. So a relatively shortcut method can be derived. So this equation can be changed to the summation xi square, okay, minus 2x bar xi plus x bar square over n minus 1. Okay? So this can be written as the summation xi square minus 2x bar can be extracted because this is the constant value and the summation xi, okay, and plus the summation of I when I is equal to n x bar square n minus 1. And in this case, this is equal to n by x bar square, right? And also, the definition of the x bar is equal to the summation of I when I is equal to n xi over n. Do you remember this equation? So, the summation of I when I is from 1 to n, xi is equal to n by x bar. Okay? So, this can be substituted with the n by x bar. Okay? Right? Because the summation of I when I is from 1 to n, xi is equal to n by n multiplied by the x bar. So this is equal to n by x bar. So this can be written as the summation of I when I is from 1 to n xi square minus, this is the 2 by n by x bar square, right? And this is the n by x bar square. So this is n by x bar square minus, okay? Right? So over n minus 1. And here, the x bar is also equal to the summation of I when I is from 1 to n xi over n. Okay? So this can be written as the summation of xi over n square. Okay? Right? So finally, this is equal to the summation of I when I is equal to 1 to n xi square minus the x can be eliminated here, okay? So that is equal to the summation of I when I is from 1 to n xi square over n over so if we use this equation, we don't have to calculate the x bar, okay? To calculate the sample variance, okay? So this is the shortcut method to calculate the sample variance s square without the calculation of the sample mean, okay? And now we are going to solve the example 6-3. This is about the sample variance by the shortcut. Please calculate the sample variance and the standard deviation using the shortcut method. Okay, this is the same test data. And now we are going to use this equation instead of this. So by using this equation, the s square is equal to 12.6 square plus 12.9 square blah 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 plus 13.1 square minus 12.6 plus 13.1 square over 7. Okay? And if you use your scientific calculator, that is equal to 1353.6 minus 104 square over 8 over 7. The answer is 0.286 pound square. Okay? So we can obtain the same answer by using this equation, and also the sample standard deviation, that is the root s square, is equal to 0.48 pound. Okay? So now we can simply calculate the sample variance and the sample standard deviation by using this shortcut method. And now we are going to discuss about the sample range. If the n observations in the sample are denoted by x1, x2, blah blah blah, xn, the sample range is given the following equation. We can say that is the R, okay? R is equal to the maximum value of the sample, xi, minus the minimum value of xi, okay? So this is the range of the sample. So from the previous example 6-3, okay, in here, what is the maximum value? That is the 13.6. What is the minimum value? That is 12.3 here. So the sample range R is equal to 13.6 minus 12.3, that is equal to 1.3. So based on this sample range, we can presume the scatterness of the data point, okay? Simply. And note that the population range should be always larger than or equal to the sample range. Why? Because sample is a part of the population. So always the population range is larger than or equal to the sample range. And this is the relationship between the population and the sample. In most statistical problems, the sample of the observations selected from the population is considered. Okay? And the population is described by the mean, mu, and standard deviation, sigma. And a random sample size n is drawn from a population, okay? Because the sample is included in the population, and it is described by the mean x bar and the standard deviation s. So this is the schematic description of the relationship between the population and the sample. The population normally has numerous samples. Okay, so the number of samples is very large, which is very close to the infinite. Okay, so we need to express the population as the line. Okay, since the number of samples is numerous. And a portion of the population is the random sample here, right? And the sample is from x1 to xn, and normally we can count the number of samples. So this sample is expressed by this histogram, okay, here. And this histogram has the mean x bar here, and the scatterness of the data is given as the standard deviation s. Okay? So normally, the sample is expressed by the histogram, and the population is expressed by the line, okay, with the mean mu and the sigma, okay. And now we are going to discuss about the stem and leaf diagram. The stem and leaf diagram is a good way to obtain an informative visual display of a data set from x1 to xn, where each number xi consists of at least 2 digits. Okay? There is a requirement as compared to the dot diagram. So what is the dot diagram? In the previous chapter 1, we have discussed about the dot diagram, right? So we have only one axis, right? And we denote the dot, okay? So based on this dot diagram, we can simply determine the average value, right? And also the scatterness when the number of data point is below 20. Do you remember that? Okay? So if the data point is larger than 20, it is very difficult to determine the average value and also the scatterness from the dot diagram. Okay? So we already have discussed about the dot diagram, but the stem and leaf diagram is a better way to display the information of the data set, okay, when the data set have at least 2 digits. Okay? So the steps to construct the stem and leaf diagram is expressed in this slide here. Firstly, we need to divide each number into 2 parts. The first one is the stem part, consisting of the leading digit, okay, and also the leaf part, and consisting of the remaining digit. And secondly, we need to list the stem value first in the vertical column, and we need to record the leaf for each observation beside its stem. And finally, we can write the units for the stems and leaves on the display. Okay? So this is the steps to construct a stem and leaf diagram. And you guys can easily understand about the stem and leaf diagram based on this example. This is example 6-4 about the alloy strength. To illustrate the construction of a stem and leaf diagram, consider the following alloy compressive strength data. This is the alloy compressive strength data, okay? This is the compressive strength of 80 alloy specimens. And the unit is pound per square inch, okay? And from this table, the minimum value is 76 here, right? This is the minimum value. And the maximum value is 245. As you can see, all the data points have at least more than 2 digits, right? So we can use the stem and leaf diagram. So this is the stem and leaf diagram. So this is the minimum, okay? So the starting point of the stem should be 7 here, okay? And the maximum value is the 245. So the last value of the stem should be 24 here. So we can fabricate the stem column here first. Then we can fabricate this leaf column here based on the remaining data, remaining digit. For example, for the case of the 76, the remaining digit is 6, right? So the value of leaf is 6 here. For the case of the stem 10 here, we have only 2 values, that is 105 here, and also the 101 here. We have only 2 values. So the values of the leaves can be 5 and 1. Okay? So we can apply the same procedure all stem and of leaf. So we can fabricate And also, we can provide the information of the frequency. That is, number of datas included in each stem. Okay? For example, for the case of the stem 7, we have only one value, that is the 76. So the frequency is 1. And for the case of the stem 10, we have two values, that is 105 and also the 101. So the frequency is 2. Okay? Right? So the frequency is the number of data points included in each stem. So from this table, we can know that the most data are between 100 and 200. Right? Which means that the compressive strengths of the alloy specimens are mostly between 100 and 200. Okay? So from this stem and leaf diagram, we can easily conclude the range of the data, which are mostly included. Okay? And also, we are going to discuss about the split stems. The purpose of the stem and leaf is to describe the data distribution graphically, okay, and or visually. And if the data points are too clustered, okay, too compacted, we can split the leaf, the stem, and we can have multiple stems. Okay? For example, we can split the stems by the 2. Okay? We can have the lower stem L, also the upper stem U. So in the case of the lower stem, the values of the leaves will be only 0, 1, 2, 3, 4. And for the case of the upper stem, the values of the leaves will be 5, 6, 7, 8, 9. Okay? We can split the stem into two parts. And also, sometimes we need to split the stem into 5 parts. Okay? If the data points are too clustered, we need to split the stems to effectively see the data point. So, first stem, that is called Z. In that case, the values of the leaves will be only 0 and 1. And also the second stem, the values of the leaves will be only 2 and 3, blah, blah, blah. And the fifth stem, in the case of the fifth stem, the values of the leaves will be only 8 and 9. Okay? So, based on this definition, we can split the stems also. And this is the example 6-5 about the chemical yield. The stem and leaf diagram for 25 observations can be given in these 3 different tables. The table A is the stems splitted, and as you can see, the data points are too compacted. Okay? It is quite difficult to determine the range of the data point which has the most data point. Okay? So, we divided the stems by 2, okay, based on the L and U. This is the lower stem, and U is the upper stem, okay, based on the previous definition. So, we can split the stems like here. And as you can see here, you can see the better distribution of the data point, okay, as compared to this one. This is too compacted. And as compared to the table A, we have the better distribution of the data, okay, by splitting the stems. And if we split the stem into 5 parts, based on the previous slide, this is too spread out, right? Some stem doesn't have any value, okay? So this is too much. So this is the best stem and leaf diagram for this case, for the case of the 25 observations, okay? So based on this concept, you can provide the best stem and leaf diagram based on your test data point, okay? And now we are going to discuss about the quartiles. If a data set is divided into 4 equal parts, the division points are called the quartile. Okay? And 25% of the data is less than Q1. That is the quartile first. Okay? And 50% of the data is less than Q2. That is the second quartile, and which is the median. And 75% of the data is less than Q3. This is the third quartile. Okay? So for the data in the previous table 6-2, we can have this another table. Okay? The Q1, 25% of the data should be less than Q1. Okay? Which means that the value of Q1 should be larger than. So in the case of the previous table 6-2, we have 80 OCW specimens. Do you remember that? Please see your previous page. We have 80 compressive strength data points from the OCW specimen. So the 25% of the 80 data point is 20 samples. Okay? So the 25% of the data should be less than Q1. This means that the value of Q1 should be larger than the 20th data point, but smaller than the 21st data point. Right? Right? Because we only have to include 25 data points in the Q1. So this is the compressive strength of the 20th compressive strength of the previous table 6-2. Okay? There is the 143. And this is the 21st compressive strength of the previous table 6-2. Okay? So the Q1 should be the average value of these two values. Okay? So in the previous table 6-2, we have total 80 data points. Okay? And in this case, we need to define the Q1. There is the quartile first. And the quartile first should be larger than the compressive strength of 20 specimen, right? And also, should be lower than the compressive strength of 21st specimen, right? So how can we define the value? That will be the average value, right? If we provide the average value of 20th, this is the average value, that is the Q1. If we apply this value, we can define this quartile first, right? Okay? So 25% of the data should be less than the Q1, and the Q1 should be the average value of 20th plus 21st compressive strength over 2, which is the average value. Okay? And also we can provide the same concept Q2 and Q3. So this is the compressive strength of 40th specimen, and this is the compressive strength of 41st specimen. Okay? So the average value is equal to 163. Okay? That is the quartile 2. And Q3 is also can be calculated by the average value of 60th and 61st. Okay? So the value of the quartile 3, Q3 is equal to 181. So if the data set is divided into 100 equal parts, this case is called the percentile. Okay? And now we are going to discuss about the interquartile range. As a simple measure of the variability, the interquartile range defined as IQR, this is the interquartile range, that is equal to Q3 minus Q1. Okay? This can be used. Okay? And from the previous table 6-2, the interquartile range is equal to, the Q3 was 181, and Q1 was 144. So the interquartile range is equal to 37, right? So based on this interquartile range, we can presume the scatterness of the data point, right? And now we are going to talk about the frequency distributions. A frequency distribution is a more compact summary of the data than a stem and leaf diagram, and it is expressed as table, graph, and or function. And the range of the data is divided into intervals called class interval, cells, or bins. Okay? And the number of bins approximately equal to the square root of the number of observations. That is the n. So, for example, in the case of the histogram, the x-axis indicates the variable, and the y-axis indicates the frequency. So for this case, we can have the histogram, right? There is the example. We can have the histogram. We can have this kind of histogram, right? And the one column is the bin. Okay? Okay? So this is the bin. So here, the number of bins, here, the number of columns in the histogram is approximately equal to the square root of the number of observations. Okay? So this can be explained in the later slide again. Okay? You can easily understand. So this is the frequency distributions from the previous table 6-2, okay? And the considerations. What is the range? Data range. This is the maximum value, and this is the minimum value. So R is equal to 169. Okay? This is the range of the data. And what is the number of bins? Based on the previous definition, that is the root n, the total number of observations, right? So the total number of observations was 80. So that is equal to 8.9, root 80. And the class width, the width, okay? This is the number of bins here. And the width of each bin should be the range divided by the number of bins, right? So that is equal to 169 over 8.9. That is equal to 8.9, 18.9. Okay? So from this consideration, we have to make the decisions, right? How we can display the data, okay? So based on this value, when we want to use this histogram, the number of bins should be the integral value, right? So we can determine the number of bins is equal to 9 because this is the closest integral with the calculated number of bins. And also, the class width is assumed to be 20, okay? Because from this, we obtain the 18.9 class width, okay? So we can determine we're going to have the class width as 20. What is the starting point? The minimum value was 76. So the starting point can be determined as 70. So from these decisions, we can fabricate this table. This is the frequency distribution for the compressive strength data in the previous table 6-2. the starting point is 70 here, and the class width is 20, which means that the first class should be between 70 and 90. Okay? And the second class should be between 90 and 110. Okay? And the last one is between the 230 and 250. Okay? So based on this distance, we can have this kind of class first. Okay? This column can be fabricated. And also, according to the previous test data, table 6-2, we can calculate the frequency for each case, each class, right? This is the number of data points included in each class. The first one is just 2, okay? The second class is 3, blah, 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 and the last class is 2. So the total frequency is equal to 80. This is the total number of data. And also, from this, we can calculate the relative frequency. What is the relative frequency? That is the frequency divided by the total frequency. Okay? So this is 2 divided by 80. And this is 3 divided by 80. Blah, blah, blah. And this is 2 divided by 80. Okay? So according to the relative frequency, we can easily see which class has the largest number of data points. Okay? And also, so in this case, the summation of the relative frequency should be equal to 1. Frequency, we also can calculate the relative frequency in the last column. Okay? So as compared to the previous stem and leaf diagram, this is more effective. Okay? And so, please remember this table. And from this table, we can describe the histograms. And the histogram will be discussed in the next class, okay?